tal? Buenas tardes. Les doy la bienvenida a esta edición del seminario del Instituto de Materiales Avanzados para la Manufactura Sostenible. Bienvenidos a todos. It is my great pleasure today to introduce Miguel Modestino, Professor of Engineering at New York University, for this seminar. Aunque Miguel es hispanoparlante, vamos a tener el seminario en inglés. Entonces voy a hacer mi breve introducción en inglés también para que todo el mundo lo pueda aprovechar. Again, it's our great pleasure to have Professor Miguel Modestino, who is Donald Othmer Associate Professor of Chemical Engineering and also the Director of the Sustainable Engineering Initiative at New York University, the Tandon School of Engineering. Miguel has a lot of achievements, so I will probably not be exhaustive in my introduction. So he is under the many awards he has received. We would certainly like to mention the MIT Technology Review Innovator Under 35 in Latin America and globally. And he has also a National Science Foundation Career Award in 2019, has raised very important funds for his research. And well, he is originally from his career education is originally from the University of California in Berkeley, where he got his PhD in chemical engineering. And he also has a part of his education from the Massachusetts Institute of Technology, where he did his master's in science and bachelor's in chemical engineering. So it is my great pleasure again to introduce, to welcome Professor Modestino. We will have to talk about 45 to 50 minutes, and we will have a space about 10 minutes at the end. So please take advantage of this opportunity to interact with Professor Modestino. Thank you very much, and please go ahead.
Thank you, Oliver. Muchas gracias a todos también por provenir a la presentación. As Oliver mentioned, I'll be doing this presentation in English for the benefit of those of you that may not be Hispanic speakers. But what I wanted to do today was just to give you a brief overview on some of the work that my group have been doing over the past 6 years here at NYU, understanding how we can use electrochemistry to bring about sustainability to chemical manufacturing. But while Oliver already gave you a brief introduction of my professional career, I always like to start my talks by telling you also a little bit about myself personally. So I was born and raised in Caracas, Venezuela, which I'm sure all of you are familiar. Venezuela is this beautiful country that have really been blessed with amazing nature in a similar way to Mexico. So here you can see some pictures from El Salto Ángel, the tallest waterfall in the world, as well as some of the wonderful beaches that we get in the Caribbean that I'm sure that many of you enjoy in your beautiful country as well. But what I usually tell people is that Venezuela also has an ecosystem that is not very well known internationally, which is really tall mountains. Venezuela gets the last little bit of the Andes coming all the way down from Chile and Argentina that make it to the western part of the country. And in this picture from about 30 years ago, you can see myself and my sister eating snow and actually seeing snow for the first time in our lives. I'm being so excited that we just decided to eat it. And this picture was taken in El Pico Simón Bolívar, which is the tallest mountain in the country. And as a matter of fact, back in the day, you were able to go up these peaks and even enjoy a day of skiing in a similar way that you would in the Alps in Europe or in the Rocky Mountains here in the US. This certainly wasn't the case when I was growing up, and it's not the case today. These mountains are so high that they're home to some of the very few tropical glaciers in the world. And when I talk about tropical glaciers, people often feel surprised because these two words usually don't go together in the same sentence. And the reason why we have glaciers is because these are very high mountains, right? And 100 years ago, we used to have 5 of them. We used to call them the 5 white eagles, like that they will overlook the country from the top and perhaps help protect it. But fast forward 100 years and they're mostly disappear. We only have about 1% of the area that they once used to cover, now covered by ice. And just to give you a sense of what this looks like, that mountain that I show you, the picture of me and my sister, back in the 60s, when my dad was born, this is what it used to look like. This is what it looks like today. So most of that ice is gone, and what is left is a tiny bit of ice in the glacier Humboldt. That is a somewhat secluded glacier in Venezuela. You need to go on a trek for about 10 days to get to it. And I tell these stories not necessarily because these are the worst impacts of climate change, and it's kind of funny to just say it after a few days of very, very dense smoke because of the wildfires in Canada that were experienced here in New York City. But this is a story that gets really close to my heart, right? Like just thinking on the future, when and if I have kids, I won't be able to take them up to these mountains and just enjoy a day in the snow in Venezuela like I used to do when I was a kid. And it's not because of like millions of Venezuelan kids went up to the mountain and ate the snow. It's because we keep using a resource that we extracted not too far from there. So in this picture from about 100 years ago, you can see the first Venezuelan oil field. So this is called Barroso II, which is an oil field that was discovered and developed by a subsidiary of Shell company. And oil was really transformational, or had been transformational for Venezuela, and I guess for many countries around the world. And it really helped us change from a small country that was primarily rural to a really modern society. And these are pictures from Caracas, my hometown, where you can see like sort of the convergence of these natural, beautiful landscapes with a really modern city. And this is basically all made out of oil. Like the oil boom in Venezuela really transitioned the country from primarily an agricultural country to, of course, an oil exporting country. And it brought tremendous prosperity to the country. So when I think about my research, I always had this conflict on like, how can we manage to support economic prosperity and economic growth without necessarily fueling climate change? And this is not news to anybody, but we all know by now that for us to mitigate the worst impacts of climate change and sort of minimize those, we're going to have to figure out a way to fully decarbonize everything that we do in society. And we're going to have to do that within the next few decades. And this is going to require tremendous investments in terms of economic investments, investments in terms of developing policies and frameworks that allow us to transition from how we're used to do things to what we actually need to do to be able to achieve full decarbonization. But ultimately, it will also rely on technology. And as engineers, we have the power to help the world transition by developing practical and deployable technologies that can help us to get there. But this is a challenging task, right? Because in order to decarbonize everything, you need to think about all of the different sectors in society, right? From the electricity that we rely on to the food that we grow, to the way that we move around, and to the way that we manufacture the things that are all around us. We're going to have to decarbonize all of these different things. And when you think about it, it might look overwhelming. What makes me feel optimistic is that we do have some technological solutions to decarbonize some of these sectors and some of the really big ones, right? We're starting to see tremendous deployments of solar and wind energy. We're starting to see a resurgence of nuclear power generation, which is yet another way to decarbonize electricity generation. In terms of agriculture, we can certainly make green fertilizers if we leverage green hydrogen production. In terms of transportation, we're starting to see the major car manufacturers fully committing to stopping the production of fossil fuel driven vehicles and the transition towards electrical vehicles, primarily driven by batteries, but also driven by hydrogen, right? By electrofuels, by fuels that we can generate using electricity. What makes me feel concerned is the fact that there are other sectors in which we don't have the technology, right? And we're going to have to invest tremendously on R&D efforts to bring this technology to fruition. And these are things like those long-term energy storage tools and technologies that allow us to then move energy from, let's say, the summer to the winter. Those technologies that will help us to decarbonize the aviation sector so that if I have to go down to Monterrey, I don't really feel terrible about the environment. And then perhaps most important among all of them, how to decarbonize all the materials that we make in industry, right? Like, and in particular, how do we decarbonize cement, steel, and the chemicals that eventually usually make it into plastics? So my group have been focusing primarily on these big sectors where we don't have solutions, because that's where we think we can have the biggest impact from an academic research standpoint, developing those solutions that, 10, 20, 30 years down the road will be hopefully available for the world to deploy as we reach full decarbonization potential. And in particular, today I want to focus around industry, because industry has some of the biggest opportunity. And as a chemical engineer that I am, we own the chemical industry, and to a certain extent, we're really responsible for this big challenge, right? The chemical industry accounts for roughly a third of the emissions in the industrial emissions, at least in the US. I think globally it's more around 20%. Most of these emissions come from the way that we make our chemicals. So today we use fossil fuel derived heat to generate chemicals, and that leads to emissions. But at the same time, the chemical industry have a tremendously positive impact in society, right? Most of the things that we make are touched in one way or another by chemicals. Here in the US, where I reside, roughly a quarter of the GDP is supported by the chemical industry. So as we think about decarbonizing this industry, we cannot think about fully stopping this industry, right? We're going to have to figure out a way to transition from an industry that is very heavy in terms of its carbon footprint to an industry that hopefully will be decarbonized at one point. And there are different ways to do this and different sectors that you have to focus on. Since this industry produces tens of thousands of chemicals, one of the first questions that comes to mind is, where do you start? And to start thinking about that question, it's useful to look at where most of the energy in this industry goes. And really quickly, you realize that most of that energy goes to make the fundamental building blocks of chemistry, which you usually make in petrochemical plants. So these are your petrochemical precursors or basic organic chemicals. I'm just listing a bunch here on the right-hand side that account for most of that energy consumption, and as such, the emissions derived from this industry. At the same time, this is an industry that took us 100 years to build. So you might be thinking, well, we have been working so hard on making these processes very, very efficient, very large scale, in a way that we can benefit from them. And that's true, but there's tremendous potential to increase the efficiency of these processes in a way that allows us to then leverage and use less energy to make the chemicals that we use today, and hopefully to do that in a decarbonized way. So in this graph, you can get a sense of how much energy is utilized for different groups of chemicals. And here's your basic organic chemicals, your petrochemicals, and plastic precursors. And what you usually see here is that today, we're actually using much more energy than we need to use if we deployed available technology, like the best-in-class technology to make the chemicals that we use today. But even if we do that, there is a big gap between what we need in our current processes and what thermodynamic limits us. And through our approach in my group, what we have been looking for is ways in which we can leverage electrochemistry to perhaps bring these points slightly down and overall build decarbonized processes that are inherently better. And by that, what I mean is processes that are more energy efficient, that are perhaps more selective, that can operate at high throughputs in a similar way than our thermochemical processes operate, that are safer. And ultimately, they're going to have to be cost competitive. And ultimately, they're going to have to be sustainable. Because otherwise, we won't be able to mitigate these impacts. So when we think about this challenge, it's useful to start thinking about what do we currently do in the chemical industry. So currently in the chemical industry, we generate heat via combustion, and we feed this heat to chemical units. So thermochemical units, some of them may be endothermic, some of them may be exothermic. We integrate heat across our plants. We separate our molecules usually via distillations, which are thermal units. And as we think about decarbonization, one of the strategies that seem to be most appropriate is electrification. And to go after this challenge, I've been leading and contributing to a team called DC Muse, which is focused on decarbonizing chemical manufacturing using sustainable electrifications. And there are multiple pathways that you can use to decarbonize chemical manufacturing via electrification. Perhaps the simplest one is just electrifying heating, right? Like we can use ohmic heating for some of the reactors that we use today, perhaps not all of them. And this is an interesting early stage solution. It won't get you additional efficiency. It won't add more than what we have today, but it will at least allow us to decarbonize. A second way that you can do this is imagining leveraging electrolyzers, like water electrolyzers that can produce hydrogen. And we can use hydrogen in a similar way that we use natural gas today, and just combust hydrogen, generate the heat required for our reactions, and produce our chemicals using thermochemical routes that we have developed today. This is also a high technology readiness level, or TRL technology, but it's one that won't allow us to improve further efficiency. It will allow us to decarbonize still. It will leverage a very interesting energy vehicle, which is hydrogen, but ultimately we'll continue to operate in the same way that we do today. Within my group, we have been focusing on the two bottom approaches that you see here, which is electrochemistry or plasma electrochemistry, which are approaches that allow you to leverage electrons directly from an electricity current, which hopefully will come from a renewable energy source, to make the products that you want. Not just to make hydrogen and then use hydrogen to produce heat, but to actually make your products directly. And the way that this looks like is start thinking about changing these thermochemical units to electrochemical units, where in electrochemistry, we need to have an oxidation and a reduction site. And we can integrate this into chemical plants that manufacture chemicals, integrate energy, now not by integrating heat, but by integrating the use of energy carriers that you can change in oxidation state in our electrochemical units, and perhaps also use electrochemistry to separate molecules. So today, I'm going to be primarily talking to you about some examples of chemical reactions that we have started to study to decarbonize this system. But if you're interested, I'm also happy to talk about some of the separation challenges that we have been going after. When it comes to reactions, one of the challenges is picking the molecule to start. And to answer that question, it's useful for us to think about what a petrochemical production network looks like. So usually in petrochemical production, we extract oil and gas, we send it to refineries, we make our fuel, which hopefully we'll stop making at some point. And then part of that oil and gas that we extracted to make fuels, we divert to make chemical precursors. And the main petrochemical precursors are things like ethylene, butadiene, and propylene. So we call these olefins, or benzene, toluene, and xylene, or BTX, which are your aromatic compounds. And then we functionalize them into molecules that are useful for us. And this is by not fully inclusive by any mean, but you're starting to see some molecules that you might recognize, right? Like polyesters, which you might be wearing, polyethylene or polypropylene, which, make all of your plastic bottles and whatnot. Things like nylon 6,6, which is a really useful material, PVC. And these are major chemical products. And every single one of these arrows that you see in this diagram is at least one reaction and perhaps a couple separation processes to make these molecules in the pure ways that we use them today. So as we think about where to start, it's also useful to think about the value added across this chain. As you go to the right-hand side, you end up with molecules that have a much higher value, a higher margin, and perhaps might be easier to deploy innovation in. As you go to the left-hand side, these are lower volume molecules, but they're very, very high volume. So their decarbonization potential is very large. But any advance that you manage to introduce in one of those processes is going to be very hard to implement, just because of the fact that the margins are very, very small. So in our research, we decided to start with a molecule here called adiponitrile, which you probably haven't heard before, but it's a central molecule for the production of material that I'm sure you have heard, which is nylon 6,6. And this is really the key bottleneck for nylon manufacturing. And one of the nice things about adiponitrile is that, we can hydrogenate it to make hexamethylene or HMDA, and then react it with adipic acid to make nylon. But to make adiponitrile, there is already a scale electrochemical processes that is used to produce more than 30% of the annual production of this molecule. And this is a process that was developed back in the 60s in industry by Monsanto company, by a brilliant chemist called Manuel Beiser, where you can take acrylonitrile and electrohydrodimerize it to make this molecule. So you start with a monomer, you make a dimer, and then this dimer can be used to manufacture nylon. And the reason we decided to start here is because of the fact that this molecule had been scaled. There's something special about the way that this chemistry is practiced in industry that can then help us understand how to percolate that knowledge across that big network that I showed you before. And to do that, we have to take a step back, go over the patent literature. There's not much scientific literature that have been published in this reaction since it was developed in industry. And what you find initially is that this reaction takes place in an electrochemical cell that is undivided. We use a multi-phase electrolyte where you have an aqueous phase that is used to dissolve your supporting ions, some chelating agents like EDTA, some surfactants like these tetracrylammonium ions, which I'll tell you more in just a little bit, and of course water. Then we add organic molecules which have some solubility in water, but it's actually quite small. So ultimately you add more of it, so you have a constant reservoir of your reactants that can then react at the surface of the cathode, where we do a reduction to make adiponitrile that then diffuses back into that organic phase. We carry out this reaction in an electrode that is made out of either cadmium or lead, which I often refer to as anti-catalysts because they have very low catalytic activity towards hydrogen evolution, which is a reaction that is competing in our network. And then on the cathode, we use a stainless steel electrode to basically oxidize water or hydroxides and generate oxygen. And ultimately, what you want to do is you're going to make this dimer at a very high selectivity, at a very high throughput, and a very high energy conversion efficiency. And selectivity is one of the key challenges here, because if any of you have worked with organic chemistry before, what you will recognize is that as you inject an electron into an organic molecule, there's multiple reactions that can take place. So if you have a couple molecules of acrylonitrile around that electron, you can do 2 electron transfer steps and generate this dimer that is your product that you want, that adiponitrile molecule, or ADN for short. If you don't have that much acrylonitrile around, what will happen is that you hydrogenate this double bond, and then you produce propionitrile, which is the main byproduct of this process. If you have way too much acrylonitrile around that electrode, you start to make trimers, tetramers, oligomers of polyacrylonitrile, which again is an interesting industrial product, but it's not what you want to make in this reactor, right? Like here, you really want to increase selectivity towards the production of adiponitrile. And if this was not enough, there's water that you can then reduce to produce hydrogen, which again is a very useful product, has a much lower value than adiponitrile. It's certainly not what you want to make in this process. Then, of course, in the anode, you generate oxygen. You have all these reactions happening inside of this cell. So during the first few years of my first PhD student, Daniela Blanco, who graduated a few years ago, what we decided to do was to focus on understanding from a fundamental engineering perspective, what is happening inside of this reactor? How do we design electrolytes? How do we operate them in a way that leads to high production rates and high selectivities towards adiponitrile? And we decided to start by looking at the electrolyte composition. And the reason why we decided to look into the electrolyte composition is because this is a very easy handle that by tuning the formulation of the electrolyte, we can control selectivity. And these electrolytes, of course, contain your organic reactants. So usually we add supporting electrolytes like phosphate buffers. They serve 2 roles. One, they support the ionic current that needs to take place inside of the electrolyzer, but they also maintain the pH of my cell in a near neutral range, which is going to be important for the selectivity of this reaction. We add some chelating agents that allow us to trap ions as they corrode away from the anode of our cell before they can get electrodeposited on the cathode and change the catalytic activity of that cathode. And then we sprinkle a little bit of magic. And that magic is these surfactant molecules, these tetracrylammonium ions that are believed to go to the interface of the electrode. They're positively charged, so they will tend to go to that electrical double layer at the interface with my cathode to block water from penetrating into that interface, enhance the solubility locally of the organic reactants, and in that way enhance the rate at which electrons are transferred to the organic reactants. So initially, we wanted to understand fundamentally what was the role of those interactions between multiple TEA ions and organic reactants in controlling selectivity. So in electrochemistry, we often run these reactions in what we call H cells, or membrane-separated cells, that allow us to run the cathodic reactions independently of the anodic reactions and really study what is happening at the interface of the electrodes that we care about. And then we get graphs that look like this. So this is a busy graph, so just bear with me as I walk you through this. So in this graph, we have selectivity, which we measure as Faradaic efficiency. And for those of you that are not familiar with electrochemistry, Faradaic efficiency is just a measure of the fraction of electrons that go to the product that you want. So ultimately, I want to just maximize selectivity or Faradaic efficiency for adiponitrile. And when we look at one of the TA ions, the tetramethyl ammonium ion, what we see here is that we can achieve some reasonable selectivity up to certain current density. And in electrochemistry, current density is directly proportional to reaction rates. So as we increase the reaction rates or current densities, then our selectivity towards adiponitrile decreases tremendously. And you see there is a very significant increase in the selectivity towards propionitrile. So that's the side product that requires only one equivalent of acrylonitrile instead of adiponitrile, which requires two equivalents of the reactant. So that was the first indication that there were some mass transport limitations that were limiting the maximum selectivity that you could achieve in adiponitrile. So, and that sort of informed further steps in the research that I'll just walk you in just a second. When we look at a series of different lengths of those alkyl side chains, what we see is that from ethyl to butyl, we see a monotonic increase in selectivity towards adiponitrile, sort of consistent with an increase interaction between my organic reactants and the side chains or the chains of these tetramethyl ions. It goes down when we get to hexyl because hexyl has a very low solubility in water. We believe that that's affecting the overall selectivity. It's also fairly high for tetramethyl, and we believe that this is because these ions are much smaller and they're more effective at solvating these intermediate radical ions. We don't really have evidence for this. We have just started to work with some molecular modeling groups to understand what is the role of that. But ultimately, it seems like these tetramethyl ions are important to enhance selectivity because they go to that interface. So we wanted to really start probing that interface and see if we could track those ions going to that interface under electrochemically relevant conditions. And to do that, we had to build cells that have a similar geometry to the H cells that I mentioned to you, but they're integrated with spectroscopic tools. So what we did is we fabricated a lot of our cells using 3D printing. This is an example of them. We fabricated a cell that allows to integrate a silicon attenuated total reflectance, or ATR crystal, which is a crystal that allows you to really do spectroscopy at the interface between the crystal and the liquid that we put on top. We deposit an electrode on top of that crystal so we can do electrochemistry. And then we are aiming to look at molecules that are close to that electrode interface by introducing currents and running FTIR experiments into this. And we can look at the presence of these tetramethyl ions by looking at signals of the stretching of the CH2 and CH3 bonds along those chains. And what we see here is that as we increase current, we actually get an increase in the absorbance coming from these bonds, which is indicative of a higher concentration locally of these molecules at that interface. And if we look at signatures of my reactant, in particular this CN stretching signal, we see that the presence of this TVA ion actually enhance its local concentration at that interface, supporting that initial hypothesis that these molecules are coming to the interface and bringing along with them some of our organic reactants that we want to react at that particular interface. So overall, through this initial study, we saw that, well, first of all, these ions are important to achieve high selectivities. We're starting to see the first indication that mass transfer limitations are really important and need to be mitigated to achieve high selectivities, which brings us to the next point, which is the natural question: if mass transport is important, can we mitigate mass transport by just increasing the concentration of acrylonitrile and reaching a higher flux of these molecules towards that interface? And the short answer to that is yes, to some extent. We did a similar set of experiments with different concentrations of acrylonitrile below their solubility limit in water and above in a two-phase media as the one that is used in our industrial reactors. And what we see is that for the low current densities, we actually see a decrease in selectivity towards adiponitrile. And we actually see an increase in the production of these other longer products, these oligomers of polyacrylonitrile, because now we actually have a very substantial amount of acrylonitrile at that interface. So as we generate radicals, the radicals propagate and start forming polymer chains. But the picture changes as soon as you increase the current density or the reaction rate, because now you're actually relying on a higher flux of the reactants close to that interface to achieve the high selectivities that you care about. So through this study, we realized that our concentration, maintaining a high concentration locally, is going to be important to mitigate those limitations. And to the extent that we can do that through electrolyte design and the way that we operate the reactors, the higher selectivity we'll be able to achieve. We did similar experiments with pH. I won't bore you with the details. I'll just mention that if you go too low, you have too much protons around, and then that just leads to hydrogen evolution. If you go too high, you have too many hydroxides around, and that ultimately leads to side reactions that take place in the bulk of the electrolyte and attack your organic reactants. Temperature plays a small role in this overall process because of the fact that usually higher temperatures tend to favor hydrogen evolution more so than they favor the selectivity towards my organic reactants. But overall, we were happy because we understood how to formulate electrolytes in a way that led to high selectivity towards adiponitrile and selectivities that were starting to reach values above 80%, which are relevant for industrial applications. But we didn't want to stop there, right? Like there's many of these molecules in this change. And, as I talk about the mission of our group is really to go one reaction at a time, trying to understand how we can introduce electrochemistry. And we want to take a step further and look to see if we could potentially use electrochemistry to produce the next molecule in the route to nylon 6,6. And this is HMDA, or hexamethylene-diamine. And this is this hydrogenated molecule where we take the nitriles and we convert them into amine groups. Currently, we do this using hydrogen, of course, at relatively high temperatures and pressure over catalytic beds. And one alternative way to do this is by using electrochemistry and doing electrochemistry in the surface of an electrode. In our case, we use a Raney-Nichols electrode. And we can operate these at atmospheric pressures and temperatures. And we can use water instead of using hydrogen directly in a way that we can perhaps reduce protons from water to generate reduced hydrogen atoms at the surface of our electrode, that instead of combining to produce hydrogen, we're going to actually have them transfer to the organic molecule to generate, well, first one amine by hydrogenating one of the nitrile groups, and then eventually two amines to generate the product that we care about. So here, the main byproduct was ACN, or this aminocapronitrol, which is the monohydrogenated dinitrile. This is the product that we want to make. But since we go through an intermediate that involves these imine groups, they can undergo an intramolecular reaction that leads to these cyclic side groups. And ultimately, we wanted to achieve the same processes. So taking the learnings from adiponitrile electrosynthesis, we decided to start thinking about how to design electrolytes to favor this reaction and avoid the byproducts, the organic byproducts, but also to avoid hydrogen evolution. So just to make a long story short, what we found here was that achieving high selectivities really require high concentrations of adiponitrile because ultimately, if we didn't have that, then hydrogen evolution started to take up. In the case of pH, here actually going to alkaline pH was much more favorable because the competition with hydrogen evolution was much stronger. Temperatures, like moderately high temperatures, seem to have a positive effect, but primarily because they increase the solubility of adiponitrile, which is the molecule that we're trying to hydrogenate. And because solubility was so important, we started to think about how to add co-solvents that can increase the solubility, like methanol. And we do that by increasing the concentration of methanol. So through a series of experiments, we're able to go from very high Faradaic efficiencies initially to, really close to 100% Faradaic efficiency or selectivities towards hydrogenation by mitigating hydrogen evolution and ensuring that those hydrogen atoms transfer directly to those nitrogen molecules. But we saw that in this case, mass transfer limitation was also limiting. Like when we look at current densities, when we go from 40 to 60 to 90, we're starting to get lower and lower selectivities as soon as you get to the high current densities. And this is consistent to what we have observed before with adiponitrile, in the sense that at higher current densities, we were getting a lower selectivity and a lower propensity for hydrogenation of the reactants. And in this case, we started to think about this challenge and how to potentially mitigate it. And the route that we decided to take was to start thinking about how we could better balance the mass transfer rates required to supply enough reactants to the interface with that electrode with the kinetic rates that are taking place at the surface of my electrode. And to do that, we rely on a very old electrochemical trick, which is pulse electrosynthesis, where we can dynamically change the potential of our reactions to accommodate the transfer of the reactants to that interface. And the way that this works is that we can apply a cathodic potential when reaction starts to take place. We start to consume our reactants, but at some point, if the concentration gets too low, we can stop. We apply a resting potential where reaction doesn't really take place. We allow the reactants to back diffuse into that interface. And as they back diffuse, their concentration goes up. And by picking the right range of pulses, we're able to control the concentration of acrylonitrile at that interface. So to run these experiments, we of course rely on multi-phase and multi-physics models to understand what is the right pulse sequence that we need to apply to modulate concentrations, and that allows us to get a sense of the range of cathodic and resting times that we had to apply in these pulses to be able to achieve an enhancement in the selectivity towards the production of this dimer. And then Daniela went back to the lab, ran a few experiments, and we observed sort of what we expected. So here we have production rates of adiponitrile as a function of cathodic times or active times of our electrodes. So if we increase the active time of our electrodes, we increase the production rate of adiponitrile. And this is not surprising because as we increase the active times, then our electrodes are active for a longer period of time, so they're able to produce more product. And then the opposite is true generally for resting times, where at higher resting times, then we produce less product. But what's kind of surprising and very exciting was the fact that there were a set of conditions where we were pulsing our electrodes, but we were able to obtain a higher selectivity towards adiponitrile than we were able to achieve with a constant operating potential, where we had a constant feed of electrons and our electrodes never stopped working. And we did that because we almost completely suppressed the side reactions that led to that hydrogenation product, to that PN byproduct. And this led to a very substantial enhancement in selectivity between adiponitrile and propionitrile. So this was a very exciting result because this is a 50-year-old process where there have been really not necessarily much visible innovation, but by just changing the dynamics of the way that we dose electrons, we can tremendously affect the product distribution of this system. But what we knew was that we don't really know all of the processes that are happening as we dynamically change this potential. What we can do is we can leverage the data that we have to understand if there is even a better potential sequence that we can apply. And this was the first incursion into the world of machine learning optimization and like how to use statistical models to help us optimize this pulse sequence. And to a certain extent, this is a fairly simple optimization problem where you have two optimization variables, which is cathodic times and resting times. And you have a target function, which is the production rate of adiponitrile. And what we can do is we can use a regression model to help guide our search for optimal cathodic and resting times. And the way that this looks like is, so here I'm just showing you the data that I showed you before, just plotted differently, where we have cathodic time in the x-axis, resting time in the y-axis. Here's our different experiments that we run. Now in colors, we have adiponitrile production rate. So here's our point of maximum production that had a 20% increase in production rate over the direct current operation. And then based on this data, we can build regressions that predict the production rate of adiponitrile under conditions that we haven't run the experiments at. And then they pointed us to areas in parameter space where we expected to have an enhancement. And when we went back to the lab, we actually achieved a substantial increase even beyond that 20%. And we did that by further suppressing the production rate of propionitrile. So full disclosure, when we were doing this optimization, we really didn't know what we were doing. This was the first time that we attempted to do machine learning optimization, and we're learning about it. Like, we know much more about it now, and I'll tell you a little bit about that. But it was an exciting result because we were able to very rapidly achieve a very high enhancement. And this got our students really, really excited. So Daniela decided to start a company together with Miriam, who you see here in the middle. The company is called Synthetics. And full disclosure, I also have financial interest in this company. It was a spin-off of my group. And initially they wanted to scale this process, this dynamic process that we develop in the group. But after a few pivots, now the company is just primarily focusing on developing software for machine learning optimization in chemical manufacturing in a way that can really accelerate these optimization campaigns. And I usually show this picture too because there's a human story behind this, right? Like, Daniela was a PhD student in my group that came from Venezuela, from Universidad Simón Bolívar, which for those of you that know is our best engineering school back in the country. And within 3 years and a half, she had a PhD. She won basically every single competition under the sun. She even got a documentary that tracks her through the progress from being a lab researcher to starting a company. And I'm tremendously proud of Daniela, who continues to run the company, raise funding, and now is actually deploying some of these solutions in some of the biggest chemicals and pharmaceutical companies in the industry. For us in our lab, this experience shows that data is really powerful. And to the extent that we can accelerate the way that we do research, the more we'll be able to accomplish. And we have started to think about autonomous workflows for this. To do that, we have been building flow reactors, as well as parallel electrochemical systems, such as the one that I'm showing you here in the video, where we can have multiple parallel electrochemical cells, which we can formulate using robotic liquid handling systems. We can then run up to 24 reactions in parallel using these parallel electrochemical reactions. Since the volumes are small, they can run, only a few minutes. We can get a lot of information. Then our robots can do all of the product extraction. They can prepare our samples for analytic assessment. And then we can run these using tools like NMRs. That we currently have a benchtop NMR in the group and have been tremendously powerful. We have also been using FTIR quite intensely, together with also, of course, chromatography tools. But with spectroscopy tools, what is interesting is that complex mixtures have complex signatures. And we have been able to leverage some of the supervised learning models to extract quantitative information about these mixtures in a way that wasn't able to be done before, especially for multi-component mixtures. And as I told you before, initially we didn't really know much about machine learning optimization. We now have really expanded these optimization approaches, which are really Bayesian optimization approaches, to integrate them with models of chemical processes in a framework which we call CHIDO, for chemically informed data-driven optimization, that leveraged some of these models to help us get to that optimal faster. And this is all in service of accelerating the research in decarbonization using electrochemistry. Ultimately, we're going to have to go through this whole network, right? Like our team, I should show you two examples. Our team have more recently started to work on ethylene and propylene, which are sort of the biggest decarbonization potential molecules in this network. We've also been thinking about how to make these molecules from biomass waste. I'll just give you a brief vignette on this work, where we're taking food waste that can be hydrothermally treated via an HDL reactor to produce biogas and hydrochar. And then this leads to an aqueous waste stream that contains these carboxylic acid molecules, which we can electrochemically decarboxylate to make olefins, and at the same time make a lot of hydrogen that we can then leverage in other processes. So through funding from the Sloan Foundation, we have undergone similar approaches where we look at the reaction networks, we focus on the molecule that we want, And then through controlling the way that we operate electrodes and controlling the way that we formulate electrolytes, leveraging similar knowledge from the previous reactions, we're able to show up to 50% Faraday efficiency to this molecule at really high current densities, like more than 90 milliamp per centimeter square, which is making this process much more attractive. And this is work that was done by my student, Andrea Angulo, who actually just graduated a few weeks ago. So I hope this gives you an example on our work on electrochemical manufacturing processes, starting from reaction understanding and developing electrolytes that can help us control selectivity, thinking about how we operate and control the operation of our reactors, and how do we integrate these with emerging tools that allow us to use active learning and automations to accelerate our research. Of course, we need a variety of tools. In our group, we go from microfluidic reactors all the way up to fairly large-scale reactors, because we have a big challenge ahead, right? Like, there's many of these molecules that we haven't worked on, but that we know rely on oxidations or reduction processes, and electrochemistry can play a role. So here's a few examples of them. Some of them we have started to work on. Some of them collaborators have started to work on. But when you look at this network perhaps more closely, what you realize is that most of these transformations are oxidation in nature. So what that means is that you're going to have to couple that oxidation with a reduction. And the simplest reduction, and the one that you certainly want to implement, is proton reduction to produce hydrogen. And there's tremendous potential in hydrogen production from chemical manufacturing using these methodologies, because if you take only the 6 biggest chemical products in industry, you can produce more hydrogen than what you need to make ammonia, which uses up to 70% of the hydrogen that we use today in the industry. So the volumes of hydrogen you can generate for industrial applications by integrating hydrogen production from electrochemical oxidations is tremendous. And hydrogen overall is a tremendous vehicle to decarbonize all of this network. This leads us to think that there's big opportunities there. And I know there is a lot of interest in hydrogen at the Tech of Monterrey. And just to give you a sense of some of the work that we have done in hydrogen, because I guess you might be interested in this work. I work in hydrogen beyond the chemical process that I showed you before for more than 10 years, right? And we have worked on approaches to generate green hydrogen directly from sunlight in the field of solar fuels, by developing prototypes of solar fuel devices, also by understanding how to design smart schemes that can be integrated with renewable grids, and how to design new electrolyzer approaches that are based on microfluidics. We have also used on how do we more effectively use hydrogen to generate energy. So my background in my PhD was in polymer physics, and we still do a lot of ion conducting membrane work or ion conducting polymer work in the group, trying to come up with new materials that can be more effective for fuel cell generation. So I'll give you a few vignettes of things that we have been doing in the past 6 years on hydrogen research, starting from the design of spatiotemporally decoupled hydrogen evolution cells. So this is a concept that our group came up with, and we patented and published here, where we can separate 2 electrochemical cells with a redox cycle in a way that we can generate hydrogen by consuming electricity when those green electrons from the sun are cheap, like in the middle of the day, but then produce oxygen at night when there is no solar energy and send electricity back to the grid. And by doing this, we can leverage arbitrage in electricity prices to lower the hydrogen production costs. So this is a direction that my group continues to be interested and involved in. Another interesting direction is by thinking about novel electrolyzer designs. And these novel electrolyzer designs are based on membraneless electrolyzer approaches, where we don't have a membrane between the 2 electrodes, but we rely on the fluidics to carry out the gases that are involved in the electrodes. So we have done a lot of work understanding multi-phase flowing electrochemical cells in order to enable this technology, which is now being scaled by our collaborators in EPFL in Switzerland. We have also worked on designing perfluorinated polymers for fuel cells and electrolyzers, and trying to enhance oxygen permeability. And we designed for the first time a perfluorinated ionomer that has an oxygen permeability that is 3 times that of naphthalene, which is the current material that is used in fuel cells. And what that means is that you can get up to 3 times the power density in a fuel cell than you do today by mitigating mass transport limitations. And more recently, we started a collaboration. We just had a meeting earlier today with a company that is being developed here in Brooklyn called Air Company, which is focused on sustainable aviation fuels. And the technology that Air Company has is based on CO2 hydrogenation to generate parafilms that can be used for fuel production. So in collaboration with us, we are trying to understand how to do this more effectively and try to understand some of the fundamental barriers behind the reactions that take place in their reactors. So hydrogen can be an interesting vehicle. And when we're talking about industry, I mentioned to you that there's other two big sectors, which is steel manufacturing and cement manufacturing. I think there's tremendous opportunities in those spaces for electrochemistry. So our group have started to recently think about ways that we can use electrochemistry at high temperature to decarbonize steel manufacturing. And there's multiple opportunities here. There's one company in the world doing this. It's called Boston Metal, where we can do electrochemistry directly in a molten oxide electrolyte that contains iron oxide. And in this way, not rely on carbon to reduce iron, and in this way avoid emissions both from the chemistry that takes place in iron manufacturing, as well as from the heat that is required for these high temperature reactors. Cement is another really interesting challenge, and I think the challenge with cement is probably going to have to be mitigated by carbon capture and utilization. Our group has published and has active funded efforts on CO2 electrochemical conversion to molecules like ethylene that can be made into propylene, or CO that can be used as syngas for sustainable fuel production, for example. And these are areas in which we plan to expand further in the future, because as we think about decarbonization, cement, steel, and chemicals are really the three big aspects that we need to focus on. So with that, I'll just close, because I know that I've been speaking for about 50 minutes by just saying a few words about my team. This work wouldn't really have been possible if it wasn't because of an amazing team. I really enjoy having a very diverse team in my group. We tend to attract really fantastic students from all around Latin America, and we'd love to see more students from Mexico and from Tech coming. So if you're interested in research opportunities, just please reach out and get in touch. And of course, all the funding agencies that have made our work possible. So with that, I'll just close, pass it on back to Oliver, and I'll change my screen just to make sure that I see your face back. And thank you.
Well, thank you very much, Miguel, for this fantastic presentation packed with information and certainly a lot of original work. And what is certainly fascinating to see is this connection with the entrepreneurship, because there's great work being done in many labs out of the world, but it very often stays there,
Yes.
producing a lot of nice papers, but you're really showing how this can come out of the laboratory. And of course, there are a lot of barriers, and many barriers that may not be technical, maybe not even economical, but political and regulatory. But of
Absolutely.
course, one has to start with something, and I think you have made tremendous progress. So that we have very little time left, but we have a few questions which are pretty specific, and I would like to read them out loud.
Sure.
Marcelo Videa asks, have you studied the performance of mixtures of the tetraalkyl ions to see if you can fine-tune selectivity? That's his first question, and the second one, I'm not sure if you can read it as well.
Yes, I can see it.
What are the counter ions in these experiments, and have anions any effect on the selectivity? So
That's an excellent question, and this is something that I think the whole community is starting to realize. Ions are very active in controlling selectivity. We have not tried mixtures. This is something that is in our radar, and that robot that I show you, we built that system for us to be able to study very complex mixtures with multiple components like those mixtures. So we can accelerate, because as soon as you start to add mixtures, then the dimensionality of the problem just explodes. So you really need more data. In terms of the counter ion, we actually published a work where we changed the cations, right? Like instead of focusing on these tetraethylammonium cations, we changed the sodium ions to potassium, cesium, rubidium, and we see that bigger ions tend to further push selectivity of adiponitrile up. And we believe it's because of their hydrophobicity, like they might actually enhance those interactions at that interface. We're seeing a similar effect in the propionic acid work that I show you at the end. And supporting ions have a tremendous power because they overwhelm basically any other ions that you have in the system. And by designing the appropriate mixtures of electrolyte, you might be able to control that microenvironment in a way that very selectively allows you to do the transformations that you want. But yeah, thanks for the question.
Thank you very much. Alfonso Crespo Yapur asks, have you considered other materials for the electrode that are good for the Volmer step, but not as good for the Tefl step?
Yeah, I mean, the short answer to that is like we haven't dwelled too deep into the materials, but like what you're getting exactly to where you need to be, right? Like we want materials that can reduce protons, but like just keep those protons in close proximity to the reactants rather than to come back and recombine and produce hydrogen. Uh, uh, we have started to think and write proposals on this space by using multi-metallics and perhaps start thinking about high entropy alloys where you have multiple metal centers that have different affinities for the different species that are required for these organic chemical reactions in a way that you can start to really promote particular steps. You can do that via that, but you can also do that via dynamics because each of these steps requires different potentials. And by tuning the times and potentials, you might be able to direct different elementary steps in the reaction in a similar way that I show you different reaction pathways. Yeah, well, thanks for the question.
Thank you. And there's the last question from our auditorium. Hello, Miguel. Thank you for your presentation. You mentioned the need to avoid H2 evolution. Have you tried a complete non-aqueous medium? I mean, this can help you to increase your potential window.
Yeah, 100%. You're 100% right. I have not. And the reason why we don't work with organic media is primarily pragmatic. And by that, I mean, if we are to deploy this process at the scales required, we're going to need to have a very inexpensive electrolyte. And whenever we start adding organic solvents, uh, just the cost of the process just goes up tremendously. And if you look at the history of that process that I show you, Monsanto started to do this in organic electrolytes like methanol. But then as soon as they decided to, they looked at they could do it with water, they completely transitioned. So my team have been focusing on the hard challenge of doing this under conditions where you have that competition because it will make the process more economic. And by doing so, will increase its potential for commercialization. That's the only reason we're doing it. For some pharmaceutical reactions, 100%. I think in that case, you don't really care too much about the price of the electrolyte and you really want to enhance the selectivity. And for those who are using organic electrolytes.
Yeah, that makes sense. Well, you already pointed to the different price sensitivity ranges on the whole spectrum, and this is certainly something to consider. One last question from my side. We saw that you've used some machine learning techniques to explore non-linear regressions. Of course, there is much more that can be done with machine learning nowadays, and I wonder if you are looking also into using machine learning, not just to do the regressions, but just also to model the processes themselves. You mentioned selectivity is obviously the key
Yeah.
here. This requires probably some ab initio modeling of the chemical process and the fusion and everything. Is this something you're looking into, or do you have any collaboration where you look
Yeah.
doing this?
So no, that's an excellent point. We don't do any molecular modeling in my group. This is an area that we collaborate for. We have a wonderful collaborator in Stony Brook University, Nidhi Rajput, that have been helping on this front. But I think there is tremendous potential there. Like I briefly mentioned our Chido approach. And in that approach, the idea is that you can start with a first principle physical model of your system that will give you a sense of what are the effects of these different parameters on reactivity, selectivity, whatever you're looking for. But if you don't have data, that's the best thing that you have. Then you use that to guide your initial search, and then as you increase data, you give more weight to the data, and you start to de-emphasize the models that might have some errors. And this, like, long story short, it helps us enhance the optimization, like we get to the optimal faster, but not by too much. And ultimately, if the models are slightly wrong or slightly off, the performance just tends to approach the performance of a purely data-driven model. But like that was the first attempt. I think there is better approaches, or we think that there may be better approaches where we use physical models to constrain our Bayesian optimization approaches, and in doing that, sort of zooming into the space much faster.
Mhm. Right. Well, it seems this is a fascinating field. You have, I'm not sure, initiated, but certainly made very important contributions to. So I think this will certainly inspire our community here at Tech. So thank you very much for inspiring us all. I guess there are people more qualified than I to take your suggestions and go back to the lab and do stuff. But well, very
That's
interesting,
right.
certainly. So thank you very much for your fabulous presentation, and hopefully we'll be in touch. Thank you very much to everybody for listening, to the organizers for putting this together, and Miguel, have a good day and a lot of success with your ongoing research.
Thank you, and thanks so much for the invitation. It was a pleasure.
Bye bye.
Have a good day there.
Hmm?